Well, it's only 9:30. I'm just going to go ahead and keep on trucking to day 15, which has been out for half an hour now. Day 15, chitin. You've almost reached the exit of the cave, but the walls are getting closer together. Your submarine can barely still fit, though. The main problem is that the walls of the cave are covered in chitins, and it would be best not to bump any of them. The cavern is large, but has a very low ceiling, restricting your motion to 2 dimensions. The shape of the cavern resembles a square. A quick scan of chitin density produces a map of risk level throughout the cave, your puzzle input. What is a chitin? I should have clicked on this before. Sometimes known as sea cradles or coat of male shells. Is it like a coral? Do they move? It says, I thought I saw the word locomotion in here, so I guess they do move around. Weird. I've never seen anything like that before. Well, I learned something today. So we have a risk level in a 2-dimensional grid. You start in the top left position, your destination is the bottom right position, and you cannot move diagonally. The number at each position is its risk level. To determine the total risk of an entire path, add up the risk levels of each position you enter. That is, don't count the risk level of your starting position unless you enter it. Leaving it adds no risk to your total. Your goal is to find a path with the lowest total risk. In a path with the lowest total risk, in this example, a path with the lowest total risk is highlighted here. The total risk of this path is 40. The starting position is never entered, so its risk is not counted. What is the lowest total risk of any path from the top left to the bottom right? Okay, great. So I think what we're looking at here is a shortest path algorithm. We are trying to move from the top left to the bottom right. And there is essentially a cost for moving from a particular square to each one of its neighbors. And that cost is equal to the cost of the neighbor. I'm trying to think if this ends up being simpler than Dijkstra's algorithm. But it's not coming to mind. So we could just crank out Dijkstra's algorithm and see where it takes us. Dijkstra's algorithm, if you're not familiar, can never spell Dijkstra correctly. Dijkstra's algorithm is just an algorithm that it's probably the sort of foundation of all shortest path algorithms. It is the shortest path algorithm. And it is guaranteed to give us an optimal solution, although it is not guaranteed to be particularly fast. Let's go ahead and start a new problem. Me pronouncing Dijkstra algorithm. Is he what is he Dutch? What is Dijkstra? I feel like that's some kind of like lowlands country. That's where that name comes from, and I don't know the actual correct pronunciation. Here in the States, I think most people will say Dijkstra. All right, so I just created a directory for this new problem. I'm going to just quickly get it ready to roll. And now we are cooking. Let's grab our input. It's pretty big. It's pretty big. So what we want to do is construct a graph. And okay, so first of all, like the actual answer that we're trying to go for is the total risk of the shortest path, right? So it is essentially, I guess we could call it the length of the shortest path, right? if we consider the length just to be the sum of all of the risk values. And if I'm not mistaken, the first risk value doesn't matter, right? Add up the risk levels of each position you enter. Okay, yeah. All right, so you can tell from that rule that they definitely are going for a kind of Dijkstra's algorithm, because what they're basically talking about is like crossing the edges between these grid cells is where the cost is. And in most graphs that I've seen, the weights are on the edges, right? Okie doke. Let's just go ahead and run Dijkstra. I struggle to. I'm not sure if I can just do this off the top of my head, so we'll be referring to Wikipedia sometimes. I've implemented Dijkstra's algorithm like multiple times, and I think there was 1 year of advent of code, maybe a couple years ago, that they were really into Dijkstra's algorithm. But it's the kind of thing that I just forget how to do if I don't use it frequently. On our normal game dev stream, we were actually implementing not only Dijkstra, but also A star, which is sort of an extension of Dijkstra's algorithm. And during that time, I got to know the algorithm really well. And now I'm just like, okay, I got to remember, like, oh, there's a priority queue. Got to make sure I update the right things at the right time. There's all kinds of like subtle things about implementing it. I think folks who are clever, maybe folks who are using like NumPy or some of the library, probably just have something that they can just whip out. I'm actually even wondering, do I have a priority queue available to me? There's a binary heap. Yeah, sure, sec. A star is like Dijkstra is a little bit like it is like a tree search, but you're not using Manhattan distance because you're just basically worrying about weights. It's not the. I think it's a little bit more like a breadth first search, but you're also trying to essentially greedily choose the shortest cumulative path so far. And then the optimization that A star does over that is that it allows you to bias not only in terms of like how far the current path is, but how far the endpoint of your current path, which hasn't reached the actual test destination yet. It allows you to bias your choice of the next thing that you search down by how far the endpoint of a path is from the destination. And what that's trying to essentially get you around in A star is like if you have like a giant like wall between if you know that your destination is up in the upper right-hand corner, it's going to bias paths that move generally towards the upper right-hand corner as opposed to paths that move away from the upper right-hand corner. Now, the search algorithm is moving, cell by cell, and it can't see walls and know that walls are there immediately the way that a human can recognize. So it may very well be that you need to go backwards before you go forwards on the optimum path. But A star, the philosophy behind that is just to say, well, you probably want to move generally towards the target, even if there are walls in your way, or even if there are like more things that will cause the graph or cause the path to become more expensive. And I believe there is some kind of optimality constraint on A star where, I don't know, if the sort of like bias factor that you add into the prioritization of which path you choose next to go down, that's called a heuristic function. And generally people will use, Manhattan distance, or they'll use Euclidean distance for the heuristic. That's, I think a lot of like game applications will just use that directly. They all have different properties. There's actually a really good exploration of this amidst game programming. A star. It's like a whole page on A star, which is fantastic. It really goes super deep into all of these like shortest path algorithms. If you're happen to be working in a representation that is a grid, let me post the link into chat. If you happen to have a graph that is representable by a grid, and you can only move north, south, east, west, there are particular hacks that you can do. I actually got into implementing this other algorithm called jump point search, which is a really, really interesting optimization. That takes way more time will take way more time for me to explain than I can, or really even not even explain. It will take me a long time to remember how it works before I could even talk about it. There are some videos in our backlog on YouTube that cover jump point search, and it's basically me and Dom, the blind leading the blind, kind of like trying to convince each other that this algorithm works. We're not going to tonight, just for this particular problem. I don't really want to do anything this complicated. It'll be enough for me to just even remember how to do Dijkstra. And I think I'm just going to be able to use a binary heap here. I'm assuming that binary heap, it just relies on some kind of ordering trait of the items that you're sticking into the binary heap. And so I'm going to have to remember how to use this in Rust. Something like, if I was writing this in JavaScript, you'd probably just like pass a comparison function into the priority queue implementation, and it would be a little bit easier to a little bit easier to work with. But in Rust, I probably will have to be doing something with like traits or something like that. Okay, so I think half the battle will just be getting the graph out of the text and into some kind of data structure that I can use. Oh, they literally provide shortest path in the docs. Oh yeah, it's totally right here. So I guess we can kind of steal this. Although I'm sort of interested in just trying to implement it, even though I'm glancing at the code here, and the structure of it like loosely seems familiar, but like I really, the way I write code, I really have to reason about it line over line, and then also pairwise reason about each line's relationship to the line above it and below it as well before I can get the things in my head. I'm going to, at least for a little while, just attempt to feel around, just try to get this implementation going, and then I'll learn something and probably forget it again. So let's go ahead and get our graph in here. And I think what we want what's interesting about this graph is that we almost don't normally what happens if you have like arbitrary graph nodes and arbitrary edges is that you have to store your kind of like list of nodes, and each of those is a list of neighbors that it connects to, and each one of those neighbors is accompanied by an attribute that is essentially the cost of navigating that edge. The thing is that like we actually have all the information that we need if we stick this into a two-dimensional array, right? Because we'll know what position we're currently on. We'll have a row and a column, or an X and Y coordinate, and then we can look directly into this table, this two-dimensional lookup table, and figure out what the cost is of going to the next neighbor. So maybe that's how we can play this. I'm trying to remember what prevents backtracking in Dijkstra's algorithm. Like if I go from node 1 to node 2, what prevents me from just like going back to node 1 in my search? Because if I can do that, then you can imagine wasting a lot of time going back and forth between the same two nodes. I think Dijkstra's algorithm assumes... I feel like it assumes that you're visiting each node only once. Right, because basically it's saying to get to a particular node, what is the shortest path that led up to this node? And what is the what is the corresponding cost of that? Yeah. So it's not like we are doing infinite depth first search. Like if we did like any kind of like, if we just treated this like as a tree, but not really a tree, but like a cyclical, a cyclical graph, then we would just like iterate forever. That's not 100% like what we're doing here. Anyways, let's go ahead and at least just like read in our table of risk factors, right? I'm just going to call it the grid, which is a vector of, it really doesn't matter, an I32, right? And let's grab our input, and we're going to split that into lines. This is a familiar pattern for us so far. We're going to map it over something, and we're going to collect it, right? And what we're mapping is a line, and for that line, we are going to split it into characters, or yes, characters, and we're going to map this into an ASCII digit, or to digit, with a radix of 10. These are all base 10 numbers. We're going to collect those into a vector. And I think that should do it. Oh, I believe this needs to be unwrapped, because you might not be able to parse a character into a digit like this. Two-digit is an option, and my braces are all confused. The method collect exists for type U32, but its trait bounds are not satisfied by U32 iterator. This one's always like, I think I'm just like missing one character here or something like that, but let's see. Splitting the lines into characters, and for each character, we're converting into a digit. Oh, and then the collect is over the map. I just moved the parenthesis by like one thing. All right. And then let's go ahead and print this bad boy, just to see what we got. That is a bewildering sequence of numbers. Let me just see if I got the last few correct. And I'm sort of willing to trust that I got it correctly if I got the last 6 characters or so. So that's 924511. Let's go all the way to the bottom. 924511. Okay, I'm just going to assume that I got that correct. Okay, right, so what we are doing is we are going to keep a priority queue of essentially cells that we have visited, or we have, we're going to have a priority queue of what we consider to be what we call the frontier. And the frontier are all the neighbors of cells that we already have the shortest path to. Okay, so that's going to be our priority queue, and the list of those neighbors is going to be sorted by how much it costs to get to that neighbor. So the initial part of our binary heap, so is it a binary heap? Yes. Let our priority queue, which is going to be mutable for sure, is equal to a binary heap. And what are we going to stick into the binary heap, really? Well, we need to know the cost of an item in the binary heap, and we also need to know its position, right? So I think we're going to have to insert structures into this. I'll just call it a node. And it's going to have some position, which is going to be a usize. And it's going to have a let's just call it the cost, which is how much it costs to get to that particular node, which is going to be U32, because we're going to be adding up a bunch of these values here. And then from here, we want to, let's just do some typical Rust stuff. We're going to derive debug. We're going to derive clone and copy. But I think in order for us to put it into a binary heap, we need to implement what? Partial equal or ORD? We need to implement ORD. We need to implement ORD and partial ORD. It's funny that I picked the word cost here because it looks like the example in the Rust docs also uses cost as well. Actually, this, like, per Shershak's recommendation, this example actually like shockingly resembles like exactly what I'm typing here, right? Oh, I probably need to import something. Implement default members. Whoa, that's not what I wanted. ORD requires ensure max, min, and clamp. Is it just that I don't have ordering in scope? Ordering is in scope. ORD. Does that also just need to be imported as well? No? It's just having a hard time with it. Oh, I need to do equal and partial equal. So I think partial equal and equal are really just about comparing the whole structure and not just the cost. Because that's what they're doing in this example. So I can derive those. Then with pause here. So this is a binary heap of nodes. And then we're going to insert add append. I don't think append is what I want. What is the operation to actually add stuff into this? Push. Okay. What are we pushing on? We're pushing on nodes. We're going to first push on the 15A input, the west neighbor, so the east neighbor and the south neighbor, right? So are we going to do X and Y or row and column? This is always like something that's going to be super confusing. Or I could be really explicit and actually make a structure that has X and Y here. Let's just call it row and column because I'm going to be indexing into this vector using row and column, right? So it's going to be row 0, column 1, which is the eastern neighbor. And the cost is grid of 0, 1, right? If grid were global, I could almost throw away this cost property and just look it up in these comparison functions. but I'm not going to do that. So let's actually call the grid the cost. So that's the first one. And then we're going to do the neighbor to the south. Oops. That's been happening to me more and more where I think I press the copy shortcut and it doesn't actually copy. Okie doke. So we've got the west one, the east one, and the south one. And what we're going to do now is start examining stuff off of the priority queue. So while let sum node equals pq dot pop. We want to look at all the neighbors. And push them onto the priority queue with their cost. Also, we want to update a neighbor if it's already in the priority queue, but we find a shorter path to it or a lower cost to it. Alternatively, we could have continued to find all the shortest paths if position equals goal. If node dot pause is equal to grid dot length. Is this a square? 100 by 100. It is a square. You know what? I'm not going to be cute about it. Let's actually just keep the width and height here. Let num rows equal cost dot length. Let num calls equals cost of 0 dot len. We know that they're probably going to be the exact same, but you know what? Let's make a general solution here. Num rows -1, num calls -1. Then we can print out our cost to get here. And we are done. Right? And if we get down here, we can panic and say that we've actually found no answer. We should never get here. So this should actually be unreachable, right? Maybe that's what we'll do. Okie doke. So now we're going to add all possible things. And then again, like I want to... I guess going backwards, is that a risk in here? If the cost is greater than the distance to the current position. Continue. Oh, I see, because we're also keeping a list of the optimal distances to each position. Right. So we can also make a hash map here where it's like let best costs or lowest costs is going to be a hash map of our position usize to a U32. And this is what prevents us from going backwards. We're going to say if let sum lowest cost equals lowest costs of, I think this is when we're iterating over neighbors, right? So this rejection here could probably go into, Well, no, we're doing that rejection here. We can get to this line of code if there's something on the we pull something off the priority queue, but something else that we pulled off to the priority queue already updated the distance to be more optimal. Got it. Okay. Not 100% convinced that this line is necessary, but let's just see. I think this requires an ampersand here. If let sum lowest cost, if lowest cost is less than node.cost, continue. I don't know if Rust would let me combine these two into one line. It sure would be nice, wouldn't it? But I'm seeing a whole lot of red there. I think the let sum has to be on its own line. It did say something about there being an experimental feature where you could do that in one line, but I'm not using a pretty old version of Rust right now, so I might not have that available to me. I think at one point I was using nightly for some reason, but I don't think that's where I'm at right now. Or I could be really using like a really old nightly, which is like the worst of all possible worlds. But who knows? Okay, so now we want to go through each one of the neighbors that we care about. And we have to make sure that we add neighbors that are available. I find that maybe it's easy to, it's maybe a little bit simpler to just create a function called neighbors of. And this returns a vector of usize. And let's pass in the number of rows, the number of columns, because it's going to matter. So if the row is greater than 0, the row is greater than 0, then we can add the north neighbor. Let's do the south one next. If it's less than num rows minus 1, we can add the south neighbor. To add some extra parentheses here to make that check out. So let's do east and west now. Or rather, this is the west neighbor, right? And I'm putting this in a separate function just because it's going to be a little bit easier to read outside of the context that I'd be using it in. Okay, so this gives us our neighbors. And now we're going to loop over them for neighbor in neighbors of our current position. This is actually node.position. The cost of the neighbor is equal to I just checked the puzzle. Can't we just compare the bottom, bottom right, and right value and choose the lowest value and move on? Or it might get stuck. Well, let's actually just compare. Let's try and like come up with a counterexample, right? So I think what you're saying is like is this problem simple enough that we can just like essentially never go backwards, right? Because I think that is the case in this sample here, right? And in the example, we never go north and we never go west, right? And it doesn't say anything in the actual problem prompt about not backtracking. So I can come up with we can come up with examples, right? Where let's do like a 4x4 or 5x5 map. And let's try to like contrive one where the path needs to go backwards, right? Like what if I did something like this, and then all of these were 9s, right? So I don't know if this is like representative of the problem input, but the lowest cost path to get to the lower right here is going south, then east, then east, then north, then east, then east, then south and south, right? So in this case, we do actually need, in our search, we do need to check the north neighbor, right? Because the cost of this path is 4 plus 4 is 9. And if we were to transition to any of these other places, we would exceed that cost. Am I missing something, though? Okay. It might be a trap if we approach it like that. But when you say if we approach it like that, do you mean just looking at the south and east neighbors? Or are you talking about my priority queue or my Dijkstra approach? Oh, talking about your approach. Okay, cool. But that's a good thing to call out, right? If they had said, you know, like you can't go backwards or something like that, or there's something about the problem design, then that would be a lot simpler, actually. I think I've done programming interviews for jobs where there was actually that restriction, which I think makes the problem quite a bit simpler. Although I'm not 100% sure. Like I think you still need to do kind of like a fill search. You still need to do like an actual search. You can't just be greedy every iteration, right? Grid, actually call this cost. I don't want to overwrite the word cost. Maybe calling this cost is a little bit too general. So I'm just going to call this grid. We know what we're talking about. So this cost here is actually the cost of this current neighbor. And I think what we were saying is we're going to do this thing again. Otherwise, we're going to shove this onto the priority queue. Neighbor and the cost is there. So one thing I'm forgetting is where do we actually update the best distance? I think we update it here, right? So we will say the lowest cost of node.pos is node.cost. Is that where they're doing it in the Rust example? Oh, they're actually doing it when they push on. So not when they pop off. I guess it can really go on at any time. Although we do want it here because we want to make sure that we don't try to add it anywhere else. Okay. Boy, I have a very low level of trust that I've written this correctly. But I think we should just go for it and see what happens. I have a warning in here. Not using binary. Okay. It's because I really wasn't trying to use it. You just added it for me. Okay, this feels like an infinite loop, right? It's just, I'm running it and it's not getting anywhere. So I think I have omitted a step or I'm including a typo somewhere. And it could be anywhere, really. When we get into programs that are this complicated, right? This is already like hundreds of lines of code. The possibilities for me making an error are really, really broad. And I also did a fair amount of copy and paste too, right? So I do want to make sure that I did this neighbors thing correctly. So I can just test it out with a few things. Gosh, though, I'm feeling so lazy about it. Let's just print out a bunch of neighbors, right? And we'll probably need to terminate this because it's going to spit out a lot of crap. Node.pause. What is it complaining about here? It doesn't have format display. Well, you can debug. You can debug print. Okay, 55.0. It's kind of funny that we're sort of like going over the same position over and over and over again. So that seems like an interesting problem. Right, I think we've hit I think we're seeing what our infinite loop is. So the neighbor is a 55.0. So this is the 55th row, column 0. We have the north neighbor here. We have the south neighbor here. And we have the east neighbor here. So maybe our neighbor processing is actually correct. Let's take a look at the very start of this output. If it's, gonna have to run it and cancel it right away if I want to get that. Did I do it? Was I able to do it, or did I blow out the buffer? Boy, all these random Mac OS click and drag side effects. I wasn't able to do it. I wasn't fast enough. I could just break after the first thing, right? Or let's break here. So for 1.0, our neighbor is 0.0.20.11. So I think probably in lowest cost, I actually need to add something to this, where lowest costs dot insert of 0.0 has a cost of 0. I don't think this is solving my bug, but it should prevent us from seeing 0.0 the next time around. Or rather, we do see the neighbors, but it shouldn't get pushed on, right? So maybe what we can do at this break is also just print out the priority queue, right? All right, so the neighbors that we were looking at are 0.0.20 and 1.1, and then what's in the priority queue is 0.1.20.11. Good, so we didn't put 0.0 back on there because this code prevented us from doing that, which is what we wanted. Now, if I get rid of this break, I don't know if we're infinite looping anymore. Either that or... we're infinite looping in a... Well, we are infinite looping, right? Because we're doing 5942 is just getting printed out like consecutively many, many times. And the way that we would get to that is if 5942 is being pushed onto the queue multiple times in a row. Yeah, so this shouldn't be happening, right? So if we're getting pushed onto the queue multiple times in a row, maybe this is less than or equal to. Okay, so that terminated. What is the comparison operator that they're using here? They're using cost is greater than lowest cost. Oh yeah, so this is a less than or equal to. It's just that they're reversing the positions here. If next.cost is strictly less than. Yeah. Okay, so this is basically saying we not only need to match the lowest cost, but we need to improve upon it. So I think that was our issue there. And this is saying that the answer is 462, which I have no idea of knowing whether it's correct or not, except for just punching it in and seeing what happens. All right, so we got that right. So there's a lot of code here, kind of a bit of a mess, but I think we sort of roughly understand what's going on here using a priority queue. Dijkstra's algorithm is always confusing because there's two different times that you look at a node. You look at a node when you pull it off the priority queue and you do some activity there. And you also look at a node when you're considering it as a neighbor of a node that you're processing in the outer loop here. And knowing what happens in each of those positions is always, to me, like super subtle and confusing and easy to kind of switch around and mess up. So for example, you can't do this I've finished check down here when you're pushing a node onto the list. And the reason for that is that you may end up finding another... This could be the first time that you've attempted to approach a particular node. Or it could be the first time you've attempted to approach the end of your path. But it could be the case that the way that you're approaching it when you get down to this line of code for the first time is not the optimal one. However, when you do pull it off the priority queue, you are guaranteed that when you pull it off the priority queue, this is going to be the optimal solution. And it took me a long, long time to be able to convince myself that that was actually correct. Let's see. Let's go ahead and add this to... Ooh, I didn't add 14b either. It's adding everything to Git right now. Being kind of annoying about it and putting everything into separate commits. But now this means that we can move on to part 2. Let's make sure that compiles. Okay, that compiles. Okay, give me part 2. Now that you know how to find out low-risk paths in the cave, you can try to find your way out. The cave is actually 5 times larger in both dimensions than you thought. The area you originally scanned is just one tile in a 5x5 tile area that forms the full map. Your original map tile repeats to the right and downward. Each time the tile repeats to the right or downward, all of its risk levels are 1 higher than the tile immediately up or left of it. However, risk levels above 9 wrap back around to 1. So if your original map had some position with a risk level of 8, then that same position on each of the 25 total tiles would be as follows. Each single digit above corresponds to the example position with a value of 8 on the top left tile. Because the full map is actually 5 times larger in both dimensions, that position appears a total of 25 times, 1 in each duplicated tile, with the values shown above. Here's the full 5 times as large version of the first example above, with the original map in the top left corner highlighted. So this is the original map highlighted, and what they're doing is taking this map, and then when you move to the left, they add 1 to everything, and the 9s wrap around. So it should be 4, 7, 1. Yeah, 4, 7, 1. And then, gosh, this is confusing. We'll see a 3 here, and so we're adding 2 in this kind of sector. We'll be adding 3 here, and we'll be adding 4 over here. And so on and so forth. So is it the case that each row, is each row the same? Or like, I guess we handle each row the same way. So what we're going to do is we're going to add 1. We're going to add 1 to each one of these values and then stamp it down in the second column, add 1 to each one of those, stamp it down in the third column, and so on and so forth. Then we go down to the second row. This second row first column chunk, this tile, is going to be the same as the first row second column tile. And then we repeat the algorithm that we did above until we go 5 by 5. Equipped with the full map, you can now find a path from the top left corner to the bottom right corner with the lowest total risk. And in this example, again, they do not do anything fancy. Because of the wraparound, I wonder if we just have to materialize the whole map. We can't just repeat the same path a bunch of times in a row. So I think the challenge here is just creating this extra large grid here, and then going from there. So let's try that out. Let's see. Yeah, we're in 15B here right now. I'm going to call this like the original grid. This is original num rows. This is original num calls. And so the challenge here is really going to just be like making sure we're not off by 1 and using our indexes correctly. So we can go ahead and create a really big vector. Let grid is equal to like a vec of vectors. So each row here is going to be 5 times 0 as U32. Actually, I think the compiler will figure it out. It's going to be 5 times the original number of columns, and it's going to be 5 times the original number of rows in here. Now let's actually build it out. So why don't we go by tiles? For tile row in 0 to 5, for tile column in 0 to 5. Let mute the increment. The row increment is, it's really just the tile row that we're talking about, and the tile column we're also adding onto that. Now what we're going to do is, now that we have the tiles, we are going to iterate over the original grid. So for r in 0 to original num rows. Let's just call it the ith row and the jth column. That's relatively conventional, right? Original num calls. Now we're copying over the original grid into the new grid. But we have to add in the row increment and the column increment. So what that means is we're going to say the grid position, and the row that we're on in the outer grid is whatever tile row we're currently on times the size of the original grid, original num rows, and the column that we're on. Oh, and then we also add I. And the column that we are is the tile column times the original number of columns plus the jth column that we're on is going to equal the value on the original grid, ith row, jth column, plus the index of the tile row that we're on, plus the index of the column that we're on, all of that modulo 10. Well, no. It goes from 1 to 9, so there are 9 total values. So we want to do it modulo 9. How do we do this? If we add modulo 9, we'll get to 0, but we really want that to wrap around to 1, right? We want 1 to map to 1. We want 1 to map to 1. But we want 10. This is so funny. This seems like a really basic kind of question. But I am trying to figure out how to not include 0 into that. So if we do modulo 10, it'll wrap around, but we'll still get 10 will be equal to 0, not 1. I guess what we could do is we could just say that, like, we could do modulo 10, and if it's 0, it's 1. Is there really no other graceful way of doing that? I feel like I'm like blanking on something super simple right now, but that's just what I'm going to do. The cost is going to be equal to this, modulo 10, and if the cost is less than, it is equal to 0, the cost is equal to 1. Boy, that is horrible, but I think that's what we're going for, and this is mutable, and these parentheses are not necessary. I think these all need to be U sizes, is that correct? Okay, so walking this over again, we are iterating over our tiles, and for each tile, we are going to iterate over the original grid, which is why we got this for I for j here. And the cost in this particular tile is whatever the cost was in the original grid, but we're also going to add the index of the tile that we're on. So if we're in the 0th row, for the 0th row of tiles, we don't add anything because of the row that we're on, but we do add something because of the column that we're on. And that will give us a number, well, it'll give us some number, but it wraps around. I don't think I can do modulo 10 here because we don't have 10 values, we have 9 values. Like, this might be something really big, right? Like, I think at most I can be adding 10 to original value, right? So if I added 10 to 9, that's 19. And the wraparound from that should be 2, right? So how do I, and so 19 modulo 10 is 9. That's not correct. 19 modulo 9, though, is 1, and if we just add 1, that's 2. So maybe what it is if the cost is greater than 9, cost equals cost modulo 9. Again, the highest value in the original grid would be 9. Oops. The highest value of tile row would be 4. And the highest row for tile column would be 4, so that's 8. 9 plus 8 is 17. 17 is greater than 9. And how will 17 wrap around? Right? 17 would be 1, 2, 3, 4, 5, 6, 7, 8, 9. 0, 1, 2, 3, 4, 5, 6, 7. And what this should be is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. So 17 modulo 9 is basically 17 minus 9. Which is 7. No. 17 minus 9 is 8, so I'm off by 1. Oh, no, wait, I'm not. It is modulo 9. I could just subtract 9. That's actually what I'm going for. Okay, so after much ado, we're going to say let num rows equals, we're going to do that up here. Let num rows equals original num rows times 5. Let num calls equals original num columns times 5. This is now the number of columns. This is now the number of rows. That gets rid of our problems, and then the rest of this stuff should be exactly the same. That took a long time, 2,846. Okay, so after all of that sort of arithmetic futzing around, I think we were able to get the right answer just by producing the new map correctly. This took... Can I time this? Took a couple seconds. I don't know, time command. That felt a lot longer than 2.4 seconds. But let's try anecdotally making the release build. All right, the release build is quite a bit faster. So if I time that, yeah, even with the cache going, it's screaming. Let's run that a few times. Let's go back to the debug build. It really takes a long time to run. It's impressive. Yeah, if we do 2.3 seconds divided by 0.18 seconds, wow, it's basically an order of magnitude faster on the release build, which is a lot more than I would have expected, to be totally honest. But anyways, so this is a fun problem. Certainly, I think one of the longer and more challenging programming problems. I was lucky that I had a good reference just looking at the implementation of Dijkstra's algorithm in the Rust manual here. This is a good kind of reference. It's a practical one. Sometimes you can do it off of Wikipedia and you're just staring at the pseudocode, and sometimes it can be hard to kind of translate this into the language that you're looking for. But in this case, I think we were, we got lucky and we were able to model the problem correctly. Okay, so that is basically going to be it. I will catch you all tomorrow.